Hello everyone, I am Pawan Kumar Sak, PhD scholar from IIT Kanpur. I am the TA for the course of Elements of Solar Energy Conversion, and today is the 11th discussion hour for this course. So in the last discussion hour, I have discussed few problems based on the photovoltaic conversion. So today we will solve some problem based on this photovoltaic conversion, and mainly these problems will be on the topic of PN junction diode. Okay. So before we start, I want to discuss that in the last discussion hour, I have solved this problem, problem number 3, and in that problem, I have taken the value of the Boltzmann constant K as 3.62 into 10 to the power minus 2 electron volt per Kelvin. But here this power should be 10 to the power minus 5. So the actual value of K is 3.62 into 10 to the power minus 5 electron volt per Kelvin. So I will solve this problem again, and then we will see some problem on PN junction diode. So in this problem, the problem has been asked that calculate the probability of finding an electron at an energy level of 8 electron volt given the Fermi energy and the temperature was given. So in this problem, the Fermi energy, that is EF, is given as 20 electron volt, and the temperature is given as 300 Kelvin, and the probability, that is at 8 electron volt, has been asked. So the formula for calculating the probability I have given in the last discussion hour, that is equal to 1 divided by 1 plus e to the power e minus ef divided by kt. So in this problem, k is the Boltzmann constant and t is the temperature. So in all the values that is needed has been given in the problem. So I am just putting these values. So E value is 8 electron volt and EF is 20 electron volt. And then this K value will be 3.62 into 10 to the power minus 5 and multiplied by the temperature, that is given as 300 Kelvin. So when you will solve this term, it will come out as 2.718. Thus the probability of having an electron at an energy level of 8 electron volt will be come out at 0.269. So this is the answer for this problem. Okay, now I will move to the next problem, that those will be based on the PN junction diode. So the first problem is consider the following two semiconductors. For semiconductor 1 EG, that is energy band gap, is given as 1.5 electron volt, and next the electron affinity is given, then the work function. And in this problem I have to draw the energy band diagram for the junction between these two semiconductors. Okay, so before start I want to discuss that what does this electron affinity and this work function mean. So electron affinity is the energy required to remove an electron from the conduction band edge to the vacuum level. Okay, so let me write this definition, and it is denoted by the term that symbol, that is chi. So this is the energy required to remove an electron from conduction band edge to the vacuum level. Okay. Next term is the work function. So work function is defined as the energy required to remove an electron from the solid to the vacuum level. So in this definition we consider that the electron will come out from the Fermi energy level. So let me write this definition for the work function, and it is noted by the term phi. Okay, so this is the energy required to remove an electron from the solid to the vacuum level. If I want to show these electron affinity and work function for a random semiconductor, then you can see that suppose this is the conduction band age at energy of EC, and this is the valence band age, that is EV, and this is the Fermi level, EF. Okay, and if this is the vacuum level, then how much energy will be required to remove an electron from the conduction band is, that will be this one. So this one is our chi, that is electron affinity, and the work function will be the energy required to remove an electron from the Fermi level, that will be this EF. Okay, so this one is phi. Now we will move to the problem and we'll see it. So in the first semiconductor one, that is given that Eg is 1.5 electron volt and electron affinity is 3.5 electron volt and work function. So first we will try to draw the Venn diagram for the semiconductor one. Okay. So for semiconductor one, Eg is given as 1.5 electron volt. This electron affinity is given as 3.5 electron volt, and the work function, that is given as 3.8 electron volt. Okay, now from here we can see or we will start to plot. Okay, so suppose this is our vacuum level, then we will see that if these are our conduction bandage and the vacuum bandage, then this will be the intrinsic Fermi level. Okay, as we don't know that this semiconductor is doped with what element. Okay, so we don't know that Fermi level for this semiconductor will be at center or towards the conduction or valence bandage. So from here we can show that this vacuum level, this is given as electron affinity, and its value is 3.5 electron volt. Then the energy band gap, that is given as E, is represented by Eg, and the value is for 1.5 electron volt. Now if we try to find this value, then this one will be the Eg by 2, and it will come out at 0.75. Now you can see that if we add this chi and this Eg by 2, then this comes out to be 3.5 plus 0.75. So this one will be 4.25. Okay, and in the function phi is given at 3.8 electron volt. Okay, so we can say that this chi plus Eg by 2 is greater than the phi. And what was the phi? Phi is the energy level difference between the vacuum level and the Fermi level for the particular semiconductor. So if this phi is less, then it means that the Fermi level for this semiconductor will be above the intrinsic Fermi level, or we can say that this Fermi level will be near to this conduction band. Okay, so this will be the Fermi level for this semiconductor, and the distance with the vacuum level and this Fermi level will be given as 3.8 electron volt. Okay, so now from here what we can conclude, that we have seen that the Fermi level is towards the conduction bandage. So as we are aware that if the Fermi level is near to the conduction bandage, then this one is our n-type semiconductor. Okay, why? Because the Fermi level is toward, or Fermi level towards the conduction edge. Okay, now we are now aware that this semiconductor one that was given in the problem is of n type. Okay, now we will move to the next semiconductor and we will see that with the given properties how this semiconductor will behave. Okay, so for semiconductor 2, the electron band gap is given as 1.2 electron volt, and the electron affinity is same, that is 3.5 electron volt. Next is the work function that is given as 4.4 electron volt. Now if we try to plot the band diagram, then suppose this one is our vacuum level and this one is our conduction bandage and this one is our valence bandage. This one will be the intrinsic Fermi level, or then this one will be our electron affinity that is given as 3.5 electron volt, and this one is the energy band gap that is 1.2 electron volt. So this distance will be the half of this and come out to be 0.6 electron volt. Now if we add this electron affinity and the energy, half of the energy bandage, then this will come out as 4.1 electron volt. Okay, and it should be also electron volt. So now in the problem phi is given as 4.4 electron volt. So we can say that the summation of this electron affinity and the half of the energy bandage is lower than the work function. What does this mean? That in this case the Fermi level for this particular semiconductor will be near to the valence band. Okay, so it will be near to this valence bandage, that is the Fermi level for this particular semiconductor. So from here we can say that the Fermi level is toward the valence bandage. Okay, and we know that if the Fermi level is near to the valence bandage, then this one will be the p-type semiconductor. So now we know that what are the type of semiconductors have been given in the problem. So semiconductor 1 is of n type and the second semiconductor is of p type. Okay, so now in the coming to the problem, in the problem it has been asked that draw an energy band diagram for the junction. So now what we have to do, that we have to make a junction for this n and p type semiconductors. Then we have to show the state of thermal equilibrium, clearly show the bandages and vacuum level, Fermi energy level in the two semiconductors. Okay, so now what will happen when we will make a junction, that we will see. So suppose this one is our n-type semiconductor and this one is our p-type semiconductor. Then what will happen, that in the n-type semiconductor the majority charge carriers will be the electrons. Charge carriers will be electrons, and in the p-type majority charge carriers will be holes. Now when we will combine these, then what will happen, that electron will start to move towards this p-type semiconductor. So electrons will start to move. And similarly, what will happen, that in the p-type the number of holes are higher, that's why the holes will move towards the n-type semiconductor. Then what will happen, that after some time in the n-type semiconductor there will be here I was saying that when this electron will move towards the p-type semiconductor from the n-type, then there will be number of holes that will be created towards this junction. And what will happen, that there will be accumulation of holes near to this edge. Similarly, what will happen, that for the p-type, as the holes is moving towards the n-type, thus it will leave a negative charge near to this edge. Now what will happen, and there will be some uh, holes and electrons. Okay, so similarly here will be some holes and this, but near to this edge there will be, in the left side there will be number of holes accumulated towards the edge, and the number of electrons will be accumulated for at the p-type semiconductor near to this edge. Okay, now what will happen, that because of this charges there will be an electric field generated, and because so this electric field will be generated for a particular distance. Okay, so this space is called as the space charge region. Okay, so here there will be some electric field, and here there will be no electric field. Similarly, in this region there will be no electric field, and these regions are called quasi-neutral region. Why quasi-neutral? Because there are charges exist, but the net charge is zero because of the presence of the electron and holes. So now in this region, also this region is called depletion region. What will happen with the bend, that because of this electric field there will be bending near to the junction. Okay, so suppose let me use some different color. So suppose this one was our n-type semiconductor and this one was our p-type semiconductor, and in the n-type the Fermi level will be near to this conduction bandage, that is the EF. Okay, for the n-type semiconductor, and for the p-type this Fermi level will be near to this conduction bandage, sorry, valence bandage. Okay, so this one for the p-type semiconductor, this one is our EC, this one is our EV. Okay, now if we will add, then we have seen that there will be some electric field near to the junction, and because of this existence of this field there will be some bending. Okay, so if we try to plot the Venn diagram for this NP type junction, then we will see that so first I am drawing the Fermi level. So as you have gone through the lectures and have uh, uh, read that there is one condition that is called the constancy of Fermi level for this junction. Okay, so if this one is EF, then what will happen for the N type? This will be the conduction band, and this one will be the valence band. So I suppose this one is our space charge region. Okay, and for the p-type semiconductor, this one will be our EFC, sorry, EC, and this one will be our this one will be our EC, and the below one will be our valence band H. So this one will be EV, and in between these space charge region, what will happen? There will be some band bending. So this one is our band bending. Okay, and there will be in between the junction. So it is not necessary that this junction will come out in the middle of this space charge region. It depends on the number of the concentration of the acceptor and the concentration of the donor. Okay, so in this region there will be band bending, and this difference, this is called the if in terms of voltage, then this one is our built-in voltage, that is noted as V0, and this one is built-in voltage. If we talk in terms of potential energy, then we can say the potential energy will be Q V0 plus minus. Okay, so this one is our potential energy. So as I have told you that in this region the electric field will not equal to 0, whereas uh, in this region, that is the right side of this space charge region, the electric field will be 0. Similarly, for the left hand side of this space charge region, the electric field will be 0. So that's all has been asked in the problem, that we have to draw this Venn diagram for this junction of this N-type semiconductor and the P-type semiconductor. Okay, so now we will move to the next problem. So in the next problem, it has been asked that a silicon sample has been doped with 10 to the power 17 arsenic atom per centimeter cube. If an identical silicon sample is doped with 9 into 10 to the power 16 boron atoms per centimeter cube, then after that it is given that if the doped samples are brought in close contact, then find out the built-in potential. Okay, so let's first start with the first doping. So the first doping is done by the arsenic. So as I have discussed also in the last class, that if we will dope from the column fourth element, then those are like phosphorus, arsenium, and antimony, that is Sb. Then there will be a donor of more number of electrons to donate, and the semiconductor will be of N-type semiconductor. So this 10 to the power 17, that we can say this is our donor concentration, that is given as 10 to the power 17 atoms per centimeter cube. Next, if we talk about the second semiconductor, then we can say that this second semiconductor is doped by the boron atoms. Okay, and this boron atoms lies in the third column. So the third column that I have told you that like boron, aluminium, gallium and indium. If the semiconductor is doped by this column third, then it will be of p-type semiconductor, and the concentration that will be the acceptor concentration. So this one is Na, that is given as 9 into 10 to the power 16 atoms per centimeter cube. Okay, now what has been asked that these semiconductors will come in contact and we have to calculate the built-in potential. Okay, so if we will bring these semiconductors near, then if we will brought these close to each other, then there will be junction. So if I say, then there may be p-n type junction, sorry, p-n junction or n-p junction. Okay, so for this p-n type semiconductor, the built-in voltage um, have been calculated and have been shown in the lecture notes. So I'm just using direct formula for this calculation. So the formula for this built-in potential is given as V naught is equal to KT divided by Q ln Na multiplied by Nd divided by the Ni square. Okay, where Na is the concentration of the acceptor and Nd is the donor concentration, whereas Ni is the intrinsic concentration carriers. And this K value for this K I have also discussed in the first problem, that is equal to this 8.62 into 10 to the power minus 5 electron volt per Kelvin, that is Boltzmann constant. Also in terms of joule, then this will be 1.38 into 10 to the power 23 joule per Kelvin. Okay, here T is the ambient temperature, so generally we take it as 300 Kelvin, and this Q is the charge of the electron. That is equal to 1.9 into 10 to the power, sorry, 1.6 into 10 to the power minus 19 coulomb. Okay, and this Ni, as I have discussed, that this Ni is intrinsic carrier concentration, and this value is equal to 1.5 into 10 to the power 10 centimeter minus cube for the semiconductor of silicon at room temperature. Okay, so now we can put all these values in the formula and we can calculate the built-in potential. So this V naught will be equal to the K, so 8.62 into 10 to the power minus 5, T is given as 300 divided by Q, that is 1 electron volt. So I have put these values in electron volt per Kelvin for the Boltzmann constant, and in the ln there will be Na, that is given in the problem as 9 into 10 to the power 16. 9 into 10 to the power 16, the donor concentration, that is given as 10 to the power 17 divided by this Ni square, that is 1.5 into 10 to the power 10 ka whole square. So when we will solve this, then this built-in potential comes out to be 0.81 volt. So that has been asked in the problem. Okay, so now we will move to the next problem. So the next problem is that the intrinsic carrier concentration is given for the silicon, and after that it has been doped with phosphorus, and it has been given that all the dopant atoms ionized and we have to calculate find out the hole concentration. So first we will solve the first part. So in the first part it has been given that this silicon atom has been doped with the phosphorus. So as I have discussed that this phosphorus belongs to the fifth column, that's why this given concentration will be of the donor concentration, and this semiconductor will be of n-type semiconductor. Okay, so this one will be the n-type semiconductor. Why? Because it has been doped by phosphorus that belongs to the column fifth. Okay, so this doped concentration is given, donor concentration, that is Nd, is 10 to the power 17. Okay, and we have to calculate the hole concentration. So now in the PN junction diode we have seen that there are majority concentration and minority charge carriers in a single semiconductor. So we have to denote, we have used different nomenclature, and I am following the similar. Okay, so this donor concentration, so this one is our atoms per centimeter cube, or we can say that this one is our electrons per centimeter cube. So this one will be for the n type, so this one will be the n naught, where this n is the denote the electron, and this n represents the n type, and the O represents the equilibrium condition. Okay, so this NNO will be equal to the donor concentration, so, and that is given as 10 to the power 17 atoms per centimeter cube. Now for a single semiconductor we have seen that the multiplication of the electron charge carriers with the holes charge carriers will be equal to this, sorry, so NO and multiplied by the holes concentration for a single semiconductor, that is PNO. This N is for the N type and P is for the holes concentration, will be equal to this Ni square. Now in this problem we have to calculate this PNO. So this PNO will come out as Ni square divided by this NO. Ni in the problem is given as 1.5 into 10 to the power 10 ka whole square, and divided by this NO. So it is equal to the 10 to the power 17. So if we will solve, then we will find that the whole concentration for this n-type semiconductor will come out as 2.25 into 10 to the power 3 holes per centimeter cube. Okay, so for this semiconductor, this hole is like minority charge carriers and the electron are the majority charge carriers. Wait a minute. Okay, so now let's move to the next part of this problem. So in the next part, if an identical silicon semiconductor is doped with 2 into 10 to the power 15 aluminum atoms per centimeter cube, and only 60% of the dopant atoms ionized. So in this semiconductor, the doping is done by this aluminum. And we know that this aluminum atom belongs to the third column. Thus, the given concentration will be for the holes. Okay, and the semiconductor will be of p-type semiconductor. Then we can write that the given concentration for the holes will be equal to the Also in sorry yeah also in the problem it has been given that only 60% of these atoms ionize. Thus the acceptor concentration will be equal to the 0.6 of the total concentration, that is 2 into 10 to the power 15 atoms per centimeter cube. So this acceptor concentration will be equal to the 1.2 into 10 to the power 15 holes per centimeter cube. Okay. Now, as we know that this one is our p-type semiconductor and these are the concentration for the holes. So for this p-type semiconductors, holes will be the majority charge carriers. Uh, these holes will be majority charge carriers, and the electrons will be our minority charge carriers. Okay, so we can say that this Na that we have represented, it will be the P, this P denotes the holes, where the second the subscript, this P denotes the holes, the subscript that denotes the P-type semiconductor, and then this naught represents the equilibrium condition. So this Pu will be equal to the acceptor concentration, that is 1.2 into 10 to the power 15 moles per centimeter cube. Now from here we can calculate the minority charge carriers, that will be the concentration of the electrons. So this Pu multiplied by this charge electron concentration for this p type at equilibrium will be equal to the Ni square. Now if we will try to find this Npu, then this will be equal to this Ni square divided by the Ppo, that will be equal to 1.5 into 10 to the power 10 ka whole square divided by this 1.2 into 10 to the power 15. So this value comes out to be 1.875 into 10 to the power 5 atoms per centimeter cube. Okay, so for the second part we have to calculate the minority carrier concentration. So we have solved this, and similarly we have solved for the first type. We have calculated the whole concentration. Now we will move to the third part. So in the third part it has been asked that if the doped samples mentioned in first and second are brought in close contact, then plot the carrier concentration profile. Okay, so now as we know all the values for the p-type, we have the values for the concentration of majority and minority charge carrier. So that will be the Ppu, that is given in the problem as 1.2 into 10 to the power 15. The minority charge carriers, those are electrons. The concentration for this is 1.875 into 10 to the power 5. Similarly, we have calculated for n-type in the first part the concentration for the holes, that is PNO, come out as 2.25 into 10 to the power 3. Yeah, correct. And the majority charge carriers, those are electrons, for this n-type semiconductor is equal to this 10 to the power 17. Okay. So with this data we can let me write that. Now we are solving the third part. So with this data we can plot this charge carrier concentration. Okay, so suppose this one is our carrier concentration and this one is our distance, that is x. Okay, then for the p type, and the majority charge carriers are holes, and the value for this is Ppu. Okay, and this Npu, that is lower, or we can say the minority charge carriers or electron, this is our Npu. Okay, and the value for this 1.875 into 10 to the power 5 electrons per centimeter cube. Okay, and this PPO is equal to 1.2 into 10 to the power 15. Those are holes per centimeter cube. Okay, similarly, so after that there will be the space charge region. Okay, and after that there will be the concentration for this holes is given as 2.25 into 10 to the power 3. So this one is our PNO, that is 2.25 into 10 to the power 3 holes per centimeter cube. And for the majority charge carriers, the concentration is an NO, that is equal to the 10 to the power 17 electrons per centimeter cube. And in between, we know that because of this presence of the electric field, there will be band bending, and the concentration will be like this one. Okay, so okay, and this one will be our junction. So this difference between the majority and charge carrier concentration, this will depend on the doper concentration, similarly for the p-type semiconductor, this will depend on the acceptor concentration. Okay, so this is our space charge region, and this one is our p-type semiconductor, and after that this one is our n-type semiconductor. So this is the carrier concentration profile for this PN type PN junction semiconductor. Now we will move to the next part. So in the next part we have to calculate the width of this space charge region of the PN junction diode. The permittivity of this silicon is given, that is 1 into 10 to the power minus 12. Okay, so for the 4 part we have to calculate this distance. This is denoted as W. Okay, so this formula for this W is given as under root of 2 epsilon V naught divided by the Q multiplied by this Na plus Nd divided by this Na Nd. Okay, where this Na and Nd are the concentration for the acceptor and donor, and this epsilon is our permissivity, and this V naught is our built-in potential. So first we have to calculate the built-in potential to calculate this width of this space charge region. Okay, so for V naught the formula I have shown you earlier, that is equal to the KT by Q ln Na plus Nd divided by this Ni square. So we have all the values for the Boltzmann constant, that is 8.62 into 10 to the power minus 5 multiplied by the 300 divided by the 1, and in the Allen term Na, that is 1.2 into 10 to the power 15. Sorry, in this V naught this will be Na multiplied by this Nd. Okay, so this one will be multiplied by the 10 to the power 17 and divided by the Ni square, that is 1.5 into 10 to the power 10 ka whole square. So when you will solve, then you will find that this built-in potential comes out to be 2.586 into 10 to the power minus 5. Okay, so this one is the value for this, and this Ln value comes out to be 27. So when you will solve, then this V naught comes out to be 0.698 volt. Okay, so now you have the value for this V naught and we can calculate the width. Okay, so this W will be equal to this 2 epsilon V naught divided by Q multiplied by the Na plus Nd divided by the Na Nd. Okay, so the permittivity of the silicon is given, that is 1 into 10 to the power minus 12. Okay, so now if we will put the values, then this epsilon is 1 into 10 to the power minus 12 multiplied by the 0.698, that is Wilton potential, divided by the Q, that is 1.6 into 10 to the power minus 19, and this whole term will be multiplied by the 1.2 into 10 to the power 15 plus 10 to the power 17. So when you will solve this, then you will find that this W value comes out to be 85.78 into 10 to the power minus 6 centimeter, or we can write it as 0.8578 into 10 to the power minus 6 meter. So if in terms of micrometer, this width of this semiconductor will come out as 0.86 micrometer. Okay, so this is the width for the space charge region when this p-type and n-type semiconductor comes encroach and make a junction. Okay, so the all the part have been solved. So that's all for today, and thank you for listening.